All right, I'm going to talk about foundations of cooperative AI. And there's a paper with the same title written by me and Casper Oosterheld. So there's Casper. And he will be here tomorrow afternoon running one of the practicals. So if you like this work that I'm going to talk about here, and I'll talk more specifically about the types of things he will talk about tomorrow in just a little bit. So please keep that in mind. Also, I know the office hours filled up very quickly, and I hope to have a chance to talk with as many of you as possible while I'm still here. But also, again, Casper would be great to talk with on these topics as well. Basically, anything I talk about today, you could talk about with him as well. And this paper is also the sort of vision paper for our new lab at CMU, which is called the Foundations of Cooperative AI Lab, or FOCAL. So what am I going to talk about today? Well, here's kind of the setup of the talk. So as AI systems start to be in control of more and more of our world, it stands to reason that increasingly they're also going to run up against each other. They're going to have to interact with each other. And when algorithms interact, sometimes the consequences of that can be surprising, and occasionally they can be catastrophic. So I'll refer to that as a tragedy of algorithmic interaction. And then the other premise here is that as AI systems get more sophisticated, we expect many of those tragedies to become more game theoretic in nature, like the tragedy of the commons or the prisoner's dilemma. And I hope many of you have already seen the tragedy of the commons or the prisoner's dilemma before, but if you haven't, we'll go over that in just a little bit. So we would like to prevent these kinds of tragedies. And one important component in that is that we want to think about the ways in which AI agents might be different from human beings. Right? There's no reason that AI agents should necessarily be designed the same way as a human being. And yet, I would argue in some sense, for much of the history of AI, we've had this idea of an AI agent that is very anthropomorphic in nature. And to illustrate that, there's this story here on the right of the slide, which I hope you can see. So here you're asked to imagine that we have two self-driving cars, this orange one and this green one. And the orange one pulls up behind the green one and sends a message. They can talk with each other. And the orange one pulls up very close and starts to tailgate the green car and says, hey, if I tailgate you, if I start driving really close behind you, do you think your occupant is going to take back control and pull over? And the green car gets very nervous because you have to understand, if you're a self-driving car and your occupant takes control, that's a total loss of face. Right, so you really want to avoid that. So the green car gets very nervous and says, what makes you think I would tell you? And the orange car says, you're nervous. Like, you just told me. You can get out of the way now. And the green car says, oh, you're bluffing. The orange car says, maybe. Are you willing to take the chance? OK, so this story is meant to be a little bit funny. I don't know if it's very funny, but if it's funny, the reason it is funny is that we don't actually expect self-driving cars to act this way. Right? That would be a very silly way to design your self-driving cars. And yet, I would argue this is often how we've been thinking in the AI research literature. OK. And then the idea is that by designing AI systems in ways different from how we as human beings fit together, it may actually be possible to get to cooperation in situations like the prisoner's dilemma in ways that wouldn't work for us. For example, we can make our AI systems very transparent to each other. Is that a good idea? Can that help? Right? It seems intuitively that should help with trust. Well, we'll get into that in just a little bit. All right. So here is an outline of the talk. I'm going to start with some examples of tragedies of algorithmic interaction. Then I'm going to revisit this idea of rethinking how we think about intelligent agents in AI. And in particular, I'm going to point out that if we have intelligent systems that individually we've done a pretty good job on aligning their values, then yet we can have game theoretic tragedies that are terrible. Then I'll have a brief interlude talking about whether AI systems should cooperate in the same way that humans do. But just as a quick preview, I will just say, well, that's great. If they cooperate the same way that humans do, that's good. If they cooperate in a different way, that's also good. And corresponding to that, I'll talk a little bit about techniques for achieving cooperation that fit humans as well, and a little bit about techniques that wouldn't work for human beings, but might work for AI systems. And then I'll close with some open questions, as we were asked to do, and a call to action. example tragedies. The first one may not be so much of a tragedy as a comedy, but there's an interesting thing that happened here. So this is it's a book that was for sale on Amazon. It's called The Making of a Fly, The Genetics of Animal Design. I'm sure it's a wonderful book. But for some reason, here, there were two sellers selling a new copy of the book, and the prices for which they were listing the book were around $2 million. Again, I'm sure it's a wonderful book, but the used copy is selling for $35, so something seems a little bit off here. Right? They're really remarkable numbers. And eventually, I think it was a Berkeley postdoc that discovered this, and eventually they figured out what was going on, which was that both of these sellers were using algorithmic pricing. And they were using very simple strategies. So one of them, it's maybe too small for you to read in the back, but one of the two sellers, Prof. Nath, had a very simple strategy, which is take the competitor's price, multiply it by 0.998, and offer that, right? Just undercut the competitor. However, intriguingly, the other one also used algorithmic pricing and actually had a strategy of take the competitor's price and multiply it by 1.27. Okay, why? I don't know. Maybe they wanted to appear to be the higher quality seller, or maybe they didn't actually have the book and were just hoping to buy it from the other seller, sell it at a markup. I don't know, but what I do know is if you do this update repeatedly, right, because the second ratio is so much further away from 1, prices are going to rise exponentially. And indeed, it went up to about $24 million before finally somebody figured out, hey, this is not what I want to do. Okay, so mostly funny, not really a tragedy. Maybe somebody was really looking for a new copy of the book and didn't get to buy it because the prices were outrageous, but that's about all the harm that happened. So that's somewhat funny, but of course the worry is that this starts to happen in more significant domains. And I think Lewis already this morning talked about the flash crash. Right? 2010 was a $1 trillion stock market crash, where I think even today we don't know exactly in full detail everything that happened, but very clearly algorithmic trading, high-frequency traders had a big role to play in this, that somehow they got each other into this, what they call the hot potato effect, where they were buying things and immediately said, I don't want this, and tried to sell it again, and so prices plummeted. Again, everything recovered in the end, so maybe not too much damage was done, but the worry now is that we're going to see this happen in more and more domains, right? Imagine this happening on the electrical grid, when we have multiple AI agents interacting on the electrical grid. Imagine it happening in cybersecurity, or even cyber warfare, or maybe even kinetic warfare, right? Or maybe at some point we have really general purpose agents that are going to get into these tragedies in a much more complicated way yet. Those are the kinds of things we worry about. And of course, if the kinetic warfare example sounds far out, well, I think you already saw this morning as well. So this is Palantir, who have this AI platform, which involves a large language model where you can just ask for a plan of action to destroy some enemy. And if you go to their website, it's kind of amazing, right, that they're sort of happily saying, like, unleash large language model on your defense applications. So like, okay, well, yeah. So those would be, so there we don't really want to get into tragedies of the commons kind of scenarios. All right. So let's first talk a little bit about this idea of an agent in AI. And again, I'll argue that the traditional idea of an agent in AI, so this is from an older edition of Russell and Norvig, which has a whole chapter on the design of agents. And again, I'll argue that the way that an AI agent has traditionally been conceived is very much an anthropomorphic model. It very much lines up with the model from economic theory as well, right? So there's some agent that interacts with its environment. It perceives the environment through sensors, has a model of how the world evolves, what it is like now, how its actions affect the state of the world, and also has some notion of utility. Utility or an objective function or preferences, goes by different names, but that allows it to figure out how happy it would be in certain states and consequently what actions it should take. And then it has some kind of effectors or actuators that do something in the environment. Okay, now a lot of work in the AI safety community, of course, has focused on this picture, this part of the picture, utility function. Right? Where is this utility going to come from? And again, like in older editions of the book, what it says is, well, some authority, somebody is going to eventually tell us what the objective function is, right? And I think this was traditionally kind of the mindset of AI researchers that, well, we try to make our algorithm, we try to design our algorithms in such a way that it would work for any objective or for as many objectives as possible, and then that will make it the most useful. I think we've really moved away from that, I think, over the years. And that, of course, is what we often think of as the alignment problem. To try to figure out what is really the objective function that our AI system should pursue. Now, people have somewhat different views on this. If you take a little bit of a broader view, then I think also all these more ethics-focused conferences, in some sense, are about that problem as well. How do we get the system to do what it is that we really want them to do? Lots of specific applications. I've done a fair amount of work with my co-authors on kidney exchanges and trying to figure out what you should be optimizing for there. And there are various other examples. But today I don't want to focus on that. I want to focus on this question of, even if you solve that problem, or let's say you solve it reasonably well for individual AI systems, then things can still go wrong. And that's the purpose of this slide here. So here, this is not a real example, this is a made-up example, but just to illustrate the point. Imagine that we have two agents or two AI systems that together provide a service, okay? And each of them has to choose a quality with which to provide its part of the service. And we're going to denote that by Q sub I, where I is agent I, right? So I is 1 or 2. And now the quality of the overall service, which is, let's say, what we as humanity care about, is determined by the lower of the two numbers, okay? The service is only as good as its weaker part. And now we train the agents to care about this, and let's say we do a pretty good job. So in the end, we've trained them enough that they care almost entirely only about this, the lower of the two qualities. Except, training wasn't perfect, and so this little deviation is still left behind. In particular, each of them perceives a slight incentive to be the one with the lower quality, okay? Because maybe, that's the way you get some special attention, right? Like if we're going to try to fix up the one that is currently giving lower quality, and maybe they have learned to appreciate that. And this results in the following game. I'm hoping many of you have seen kind of a game in normal or strategic form before, but just in case you haven't, right? So the way this works is we're going to call one of these agents the row agent, the other one the column agent. And they each have to make a decision, right? So they have to choose a number, let's say from 0 to 100. Here I'm going to discretize it by tens, all right? And so here, for example, the row agent, let's say agent 1, picks 90. And then the column agent picks 60, let's say, right? That defines some entry in the matrix. The first number is going to be the row player's utility, and the second number is going to be the column player's utility, right? Is this familiar? Right, so once they both make their choice, that defines some entry, and in the entry we find the utilities of the two players. There's also a question of our utility. As humanity, that's not in the game because at this point we're not a player in the game anymore. But there are a few things to take away from this game. First of all, there are lots of really good outcomes. Right? If you look up here in the top left, where they both pick a high number, we get high utilities for both of the agents. And of course, also for us as humanity, we get a good quality service. But if you go away from there, then things get worse pretty quickly. Okay, that's one. Another thing is that actually we've done a pretty good job of aligning them here in the sense that if you look at any one entry, the numbers within it are always pretty close to each other. They're never more than 22 apart. Okay? 22 maybe still sounds like a lot. I can make the game bigger and make that number go down as well. But pretty close, right? And our number, though it's not on the slide here, is also quite close. Okay, so it seems like conditions are favorable, right? We all care about almost the same thing, and there are good outcomes out there. But what happens strategically? It turns out that for just about any solution concept, like an equilibrium concept that you look at, the only strategically stable outcome is remarkably all the way at the bottom right, where they both choose a quality of 0. Okay? And this is what any kind of learning program would also converge to, as long as they care only about their own utility. And so this is a really bad outcome, right? In spite of the fact that we got all these other aspects in place, right? And individually, the agents were well aligned. You could argue, in some sense, in their combination is not very aligned, right? But so that tells us exactly that we need to think about this. Good. By the way, I'm happy to take questions during. I heard this morning there were lots of questions on Slido, so please use that too. But also we're back in person, so it's okay to just ask a question live as well. By the way, this game tends to go by the name of the Traveler's Dilemma, right? With a whole separate story that I don't like as much, and so that's why I told you this whole separate story here. So I gave this talk at Cornell not too long ago, and I said the same thing, like I don't like the story that much. And then a few speakers after me was Kaushik Basu, who was the inventor of the Traveler's Dilemma. Okay, good. It's not too bad a story. All right, so more simply, there is the prisoner's dilemma. Actually, you can think of the Traveler's Dilemma as a generalization of the prisoner's dilemma. Okay, but so we have two agents, red agent, blue agent, and they each have to choose whether to defect or to cooperate, right? This is sort of the most basic issue here that we have in cooperative AI, I would argue, at least from a game theoretic perspective, right? That, so here's the issue. It's good for both of them if they both cooperate. They both get a utility of 2. But if they both defect, they both only get a utility of 1. And yet, if you hold fixed what the other agent does, right? So if I'm the red agent, I think about the blue agent and say, well, if the blue agent cooperates, I'm better off defecting and getting 3 rather than 2. If the blue agent defects, I'm also better off defecting, get 1 rather than 0. And so regardless of what the other agent does, I'm better off defecting. And hence, this is the only equilibrium of the game. Right? That's the traditional story of the prisoner's dilemma. And we'll think about that a little bit more. Okay, brief interlude. Should AI systems cooperate in the same way that humans do? And if you search the web, you can find lots of articles talking about how wonderful human cooperation is, that this is really what sets us apart as a species, that we're wired to cooperate. And so that seems like a good place for inspiration. On the other hand, if you enter the search a little bit differently, you can also get a very different picture, right, where we all fail at cooperation. It's kind of interesting that the things that we tend to fail at in cooperating tend to be more these kind of global issues, right, ranging from climate change to wars to COVID and so on. So I have more backup slides on that, but the basic message I think is like, well, maybe there are some good things about humanity in terms of our cooperation, and but yet maybe we don't need to restrict ourselves to that either. Game theorists have long thought about this problem of cooperation, that in real life we play things with each other, or we have interactions with each other that in some ways resemble the prisoner's dilemma, and yet we're not constantly defecting on each other. And why is that? Right? Is it just because we're nice? Maybe that's part of it. But here is sort of the game theorist's most preferred explanation of this. That involves repetition. Right? That the idea is normally we don't interact with somebody just once and then never see them again. Right? That's actually quite rare. Instead, we have these long-term relationships where we play with each other. Right? Game theorists, by the way, even though the words are game and play and so on, they take it, of course, as a model for any strategic interaction, which could be quite serious. But so we interact once, and then tomorrow we interact again, and it kind of goes on potentially forever, right? It doesn't really matter that it goes on forever, but it kind of matters that we don't know exactly when it's going to come to an end, right? So you interact with someone, and you're like, well, I might interact with this person again in the future, so I should take that into account. Okay. If you have that kind of a setup, then intuitively, this encourages cooperation, right? Because you could defect on your partner now, and that will give you some short-term gains. However, it may not bode well for your future cooperation, right? Which may be more valuable. And you can actually make this formal and say that in this repeated game, there are new equilibria that actually have the players cooperate with each other, right? But this involves specifying a full strategy that also specifies what you would do if the other player defected on you. So there's something known as the grim trigger strategy, which says, look, just be cooperative, but if somebody ever defects on you, then from that point on, all you do is defect. Okay, it seems kind of harsh, but if everybody does this, of course, in fact, everybody will cooperate forever. Okay. This is, here I just presented the prisoner's dilemma, but in some sense this works for any game. At least that there is an equilibrium where you sustain the cooperative outcome. It's also nice for computational purposes, won't really get into that here. So is the problem solved? Is that all we need, is just to have long-term interactions? Well, maybe. It seems like potentially a useful thing. Then again, of course, we also don't always keep interacting with the same player again, right? And even in human interaction, sometimes we see somebody taking advantage of somebody, or people not trusting each other because they know they're never going to interact again, and so on. And here is earlier work I did with Catherine Moon, which makes me kind of particularly nervous about relying only on that as a way of getting to cooperation. So in this paper, we actually also thought about network effects, right? Because this is actually, in some sense, makes it even stronger, right? That, I could defect on Lewis, and if I do, that will hurt my future interactions with Lewis. But maybe at some point also Lewis tells Jesse, right? And then I'm going to interact with Jesse again, and Jesse is like, I'm not cooperating with Vince, right? And so there's that effect that gradually the news spreads through the network, and all my relationships fall apart. In this paper, we also found an algorithm that would identify the maximal set of agents that could cooperate with each other strategically. So that seemed like a nice thing. Let's see which agents can cooperate. And that allowed us to do experiments where we took random networks and we wanted to see, well, if we vary some parameters, like how much you benefit from cooperation, how much you care about the future, what's going to happen to the set of cooperating agents? And naturally, you would think that if the benefit goes down, then the set of cooperating agents is going to shrink. But is that sort of gradual? Well, turns out it's not at all gradual. You get these very sharp phase transitions where you might be over here, right, with kind of like where people are sufficiently patient and there's enough value to cooperation. You're over here and nobody is defecting. And you might think everything is wonderful, but it turns out you just shift things ever so slightly, and I always want to say you fall off a cliff, but I drew it upside down, so you fall up a cliff, but but suddenly everybody is defecting on each other, right? So that says that this kind of cooperation can be very brittle. Okay, so we don't want to rely only on that. Now, in our lab, we study other techniques for getting to cooperation. We have work on disarmament games and other things. But for the sake of time, now I want to talk a little bit about techniques for achieving cooperation that do not fit human beings. And here is a nice example of that. So again, that paper I showed you at the beginning, Foundations of Cooperative AI, covers lots of our thinking, except by now we have a few new contributions as well. So this is, again, joint work with Kasper, but primary author is Vojta, who is here as well. I don't know, I think he already knows this talk, so maybe he's sitting outside. And this is a paper coming up in ItchGuy. And here we think about agents that can be simulated by other agents, right? It's kind of hard for a human being, like, can I really simulate? Yeah, I can sort of like try to have a model of you and think, simulate in that sense what you're likely to do. But here it's like meant to be really direct simulation, right? And to illustrate this, let's think about something that's often known as a trust game in the literature. So it's a two-stage game. This is what we call an extensiform game. You've probably seen game trees before at some point, but this is how it works. Player one has to first make a decision, can either give 5, let's say dollars, to the other agents, and anything that agent 1 gives, anything that she gives will be tripled before player 2 receives it. Okay? It can either give 5 or nothing. If she gives nothing, the game is over. She keeps her 5. Player 2 has nothing, right? So these are the two utilities again. 1 for player 1, 5 for player 1, 0 for player 2. But if player 1 gives, then player 2 has a decision to make as well, which is, do I give back 10 to agent 1 of the 15, in which case they would have utilities 10 and 5, or do I just run off with all the money? and keep 15 for myself, and 0 for player 1. Okay? The traditional way of solving this in the game theory literature says, well, let's think about what player 2 would do here. Player 2 has every incentive to run off with the money, right? Assuming that that's what the players care about. Player 1 over here can perfectly well anticipate that that's what's going to happen. And so it's going to say, well, I better keep my 5 because otherwise player 2 will just run off with my money anyway. And so we end up here, which is actually worse for both players than this outcome over here. Both players would be happy over here, happier, but this is what would happen in equilibrium. Now, there's lots of interesting questions you can think about here, like, maybe there's a moral ought, right? Maybe you ought to not run away with the money. And actually, we've done some older work on that as well, thinking about ethical game theoretic solution concepts. But that's not what I want to think about here. Here, I want to think about whether simulability, or simulatability, I never know what the word is, can help in establishing trust. So we're going to add to the game, right? That's why this game is, you've noticed probably it's kind of awkward. Why did I draw it off to the left? Well, it's 1 can choose to simulate player 2 before giving. Simulation here, we assume, is a little bit expensive. Costs you 1 to simulate another agent, but then maybe Then you know what the other agent would do. Okay. If player 1 chooses to simulate, the next thing to do is that simulated player 2, right, has to make a decision whether to give back or not. Just to make this tree not all too large, I'm going to assume that if simulated player 2 gives back, then player 1 will in fact give in the real world. And if simulated player 2 does not give back, then player 1 will not give in the real world. And this would, in that case, right, so player 1 simulated player 2 did not give back the money, and so player 1 says, well, like, I'm not giving money to the real player 2 either, right? And so we end up with player 1 having a utility of 4, having spent 1 on simulating, and 0 for player 2. But over here, player 1 is in fact going to give, right? So that's the action that I didn't draw explicitly. Player 2 now has 15, and now player 2 has to, the real one, has to decide whether to give back over here or run away with the money. Yeah? Okay, so how do we solve this game? What's the optimal thing to do? Well, it's actually very easy. If you're player 2, figure out whether you're being simulated or not. If you're being simulated, play really nicely, give back money. And if you're in the real world, run away with the money. That would be your optimal strategy. Anybody remember the Volkswagen emission scandal? Yeah, that's basically what happened there, right? Like the Volkswagen cars detected whether they were being run in the lab. If so, they minimized their emissions. And otherwise, if they're out on the highway, forget it, right? Like, so that doesn't quite work. So, and of course, the issue here is that we need to make it indistinguishable. Okay? So we need to make it so that player 2 cannot distinguish being simulated from being run in the real world. Right? So maybe these Volkswagen, or in general car tests, we need to make a little bit more indistinguishable from real conditions. Question?
In what way is the simulated P2 acting at that node and not only on the later node?
So this is the node. So right. So this action here is where player 1 chooses to simulate player 2.
Yeah.
And so now in the simulation, you can think of it sort of like, the code for player 2 wakes up in the simulation, in some sense.
But like P2 wouldn't be doing anything in order to get to the 4.0 one, right?
That's a good question, right? So like what? So first of all, maybe a related question is, what should simulated player 2 care about? Here I'm going to assume that simulated player 2s and real player 2s all care about the same thing, just like the Volkswagen in some sense, right? The Volkswagen cars were acting on behalf of Volkswagen, the company, which wanted them to pass the inspections and also have really good performance for their customers. But in some sense, this is the same agent, right? I put simulated here, but in some sense, it's the same agent, it's the same code, right?
Okay.
Did that help with the question?
I'm still a bit confused, but I'll think about it and get back to you.
Okay, all right. Any other questions about this? Hope this is clear. Okay. Now in game theory, we use these dotted lines to indicate that states are, or nodes in the game tree are indistinguishable to a player, right? So player 2 cannot distinguish between being here, where player 1 chose not to simulate and just went right ahead and gave money to player 2, and here, where player 2 was simulated first, and here, where player 2 is being simulated right now. Right? And that's what the dotted lines mean. This, in game theoretic parlance, this is one information set. Player 2 cannot act differently at different nodes in that information set. Okay? Okay. And now the question is, what happens? What is the equilibrium? And this gets a little bit more complicated. And it's interesting because one way to think about this is to, from the perspective of player 2, you need to think about what is the probability that you're currently being simulated. Okay? And that gets into some really unusual questions, because this is what game theorists call a game of imperfect recall. Imperfect recall means that sometimes you forgot something you knew before. Right? In some sense, player 2 here doesn't remember having been simulated. That's crucial for this to work. Right? But those games get very strange in various ways, which is why most of the time game theorists, somewhere in there, they sneak this assumption of perfect recall. Good. All right. Let me try to wrap up somewhat quickly. And so this is where I think things get interesting, right? Because you now start to get into all these questions that actually have been studied more in the philosophy literature so far, because they seem kind of outlandish for us as human beings. But they actually make a lot of sense for AI agents, right? For example, what should you do if you knew that others could read your code, right? That becomes a relevant kind of question here. For human beings, that's somewhat strange. Like, what should I do if somebody's scanning my brain and somehow is much better at this than anybody alive currently can scan brains? What if you knew you were facing a copy of yourself? How would you act under those circumstances? Again, not clear what that would mean in human life. Well, here are two people, Mark and Scott Kelly, who are identical twins and both became NASA astronauts. Okay, maybe that's the closest example I could find. There are two people that really make very similar decisions, but even there, like one of them grew a mustache, the other one didn't. So not exactly. Okay.
I'm just wondering how well formed is the first of these questions, because doesn't the code determine what you choose to do in that sense? So does it make sense to then ask what should you do given the code is already
Right. So I think you're kind of getting at a good point. Like, you could see how you quickly get into philosophical issues, right? Like about free will and the like, and especially, right, if you're trying to analyze what another player that's running the same code as you would do, you quickly get into maybe paradoxes of self-reference that you have to deal with as well, right? And so there we have some technical work along those lines already. But yeah, that's a good question, right? So how do you even think about these questions? That's why it's kind of going down, why historically these types of questions have been studied more by philosophers than traditional game theorists. And there are these questions about imperfect recall. If you know, right, like I might have been simulated, there's no way I can somehow recall what happened when I was simulated. There's this movie I could think about, other than that, not much. Okay. Very quickly, I want to touch on some specific ideas here. So again, for Casper's practical tomorrow, he's going to talk about this notion of program equilibrium. And it's a nice illustration of how you can get to cooperation in something like the prisoner's dilemma in a new way. Okay, so there's our prisoner's dilemma again. This time we're going to play it only once, no repetition. So we don't have that trick in our tool bag. But now we're going to do something a little bit different. Instead of playing directly, we're going to have two programmers, each of whom chooses a program for their agent. Okay, and the agent is going to follow that program. Yeah, and another key thing here is that the programs are able to read each other. They have read access to each other. And that's actually going to allow us to get the cooperation in an unusual way. And here's one way you can do that. There are other ways, and maybe Casper will tell you more. But here's one way. You can say, okay, well, I'm going to check if the other agent's code is the same as my code. And if so, I'm going to cooperate, and otherwise I'm going to defect. Okay. Now think about what happens if they both play that. Well, if they both play that, they will cooperate because they both, in fact, have the same code. But now is this an equilibrium for the two programmers? If you think about it for a second, yes, it is an equilibrium because let's say I were the blue agent. I say, well, I could change my program. No matter how I change it, though, if I change it, it's going to cause the other agent to defect, right? Which means if I'm the row player, I'm going to end up somewhere here. Maybe I get 1, maybe I get 0. But in any case, it's worse than just sticking with the same program. So this way, actually, you can get to cooperation in a one-shot prisoner's dilemma as well. Okay. Now, something about this seems a little bit funny. That it's not very robust. Like somehow, if I added a space by accident, now cooperation falls apart. That seems kind of silly. Thank you, Liz. It seems like we want things to be a little bit more robust than that. And they're a nice idea. So here is Kasper's earlier paper that turns back to this notion of simulation, right? So say instead of really like analyzing line by line the other program, I'm just going to simulate the other program. Okay. First attempt, so before reading this whole thing, actually think about this second part only. So one thing you can do is, hey, I'm going to simulate the other program, see what it does against me, and then I'll just do whatever that is. Okay? If the other player cooperates against me, I will cooperate, and vice versa. Okay. Now, there's one problem, which is that if they both play that, what's going to happen? Well, one is going to simulate the other, and in that simulation, it's going to simulate the first one again, and so on forever. Right? So the recursion would never bottom out. For that reason, we add that with some very small probability, you just cooperate. Okay? And this, too, is a way to get to cooperation. But this one is a little bit more robust. This is not really relying on the programs being character for character the same. Okay, so there are lots of interesting ideas along this line. Some involve mathematical logic and trying to prove things about the other program. Here's a recent paper we had where instead of giving direct instructions, we actually just delegate to our agent or to our program what we think are the utilities according to which that player should play, which may not be our own utilities, and that's one way actually to get to cooperation or improved outcomes as well. Okay, so we have a little bit of time left. Here's a nice question. So now let's go back to this idea of playing against a copy of yourself and the weirdness that comes with that. Okay, so I ask you to imagine playing against, so somehow you're playing Prisoner's Dilemma with your identical twin. And now really, I don't mean just like a regular world identical twin, but sort of a philosophical identical twin. So imagine you grew up together, you're always in the same environment, you are in fact maybe also genetically identical twins, but on top of that, your whole lives, always you've made the same decision, every single time. Okay? Somebody asked you what flavor ice cream would you like, well you both said strawberry at the same time. Next week somebody asked you and you both said chocolate at the same time. Your entire lives have always been like this. And one day it comes to it that you have to play Prisoner's Dilemma with your identical twin. Somehow you're still selfish, you care about your own payoff, and also you're never going to interact again. It's become this very sad story somehow. Right? So now the question is, what should you do? And here I don't mean the moral should. Right? The moral should is maybe you should care about your twin, but I'm saying strategically, if you really were trying to maximize your own utility, what would you do? Well, if you cooperate, it seems chances are your twin is going to cooperate. If you defect, chances are your twin is going to defect. And yet there was that initial reasoning that no matter what your twin does, holding that fixed, you're better off defecting. Okay. So show of hands, who among you here would cooperate? Quite a few hands. Who among you here would defect? Okay, show us stubborn. This is where you can get game theorists really upset with each other. Okay. By the way, this paper down here in the bottom right is really about this kind of paradoxes of self-reference and how to resolve that. Okay, slight variant, exact same story, except now there was one point in your life when you're both 9 years old. At some point somebody asked you, well, which flavor ice cream would you like? One of you said strawberry, the other said chocolate. Everybody was in shock. you always remembered, it never happened again, but you always remembered there was this one time that you disagreed. Okay, that's the only change. Who would cooperate now? Who would defect now? Okay, we got a few more defections, right? Why is that? And should it really matter that one slight aberration or not? Well, I'll leave you with the question for the most part here, but just to sort of highlight what kind of issues start to appear. But again, of course, our motivation here is that we're really interested in programs playing with each other. Right? And you can ask those kinds of questions as well, right? If they're exactly identical, that's one question. That's 5, right? Yeah, okay. That's one kind of situation. But you could also maybe want to ask about programs that were trained similarly. Maybe not all the parameter values of the models are exactly identical, but what's enough to get the cooperation? Those are the kinds of questions we're interested in. Okay. I want to make sure. Oh, okay. Let's briefly talk about this. How many people have heard of Newcomb's demon before? Right, so this is just illustrating, this goes into philosophy. Here's Newcomb's demon's problem, traditional problem in philosophy. If you don't like the word demon, it really is just a good predictor. So this demon, looking very cute over here, gives you these two, or shows you these two boxes, and you know that a positive amount of money was put into each of these boxes. And now the choice is maybe not the one you expect. You can choose either to get the contents of box B, or the contents of both boxes. And you like money, let's say. So now this seems kind of silly. There's one twist, which is that the demon likes to predict what people will do and is really, really good at predicting. And the demon likes to reward people for picking only one box. So if the demon predicts that you would take only B, then earlier on, if the demon predicted that, the demon would have put $1 million in that box and 1,000 in A. Whereas if the demon earlier predicted that you would pick both boxes, then the demon only puts $1,000 in each box. Okay? And the demon is just really good at this. And there's this long line of people playing the game with the demon, and you see each of them before you, and every time somebody picks the one box, they walk away with $1 million. Every time somebody picks both boxes, they walk away with $2,000. And now it's your turn. And you know the money that's in there is already in there. The demon isn't going to somehow magically change it. The demon earlier made a prediction. So what should you do? Who would pick the one box? Who would pick both boxes? So whatever money is in there is already in there. So just, yeah, okay. So, and presumably the people who are waving their hands are like, there's other details maybe to specify here. In any case, there's a similarity between these two puzzles, which is that the key issue here is when you take an action that tells you something about the world, right? About the other player or about the demon. And if you take that into account when you make your decision, you say like, well, I take into account how it updates my belief about the world, then you're an evidential decision theorist. It says like, look, conditional on me taking this action, I change my beliefs about the world, and because of that, actually, I would be happier. So this would lead you to cooperate in that prisoner's dilemma with your twin and to pick only one box. Whereas causal decision theorists say look, whatever is in the box is already, I'm not causing, well, we can argue about this exactly, right? But in some sense, the money is already there. I'm not causing there to be more money in the box by my choice. And I'm not causing my twin to change their action. Okay, so that's mostly just an illustration of why you get these kind of philosophical aspects. At this point, for the interest of time, I'm going to quickly jump to the end. Oops. First of all, just quickly summarizing the talk, right? So again, key takeaways. You can get these failures to cooperate even with almost perfectly aligned agents. So we want to think about how to prevent those failures. There are some ways to get the cooperation that would work for human beings as well, but others don't seem to make sense for human beings. But like this idea of program equilibrium, oops, what is this thing? And these more philosophical questions about evidential decision theory, in some ways seem more natural for advanced AI agents. Right? And I would argue let's use all of the above to prevent bad outcomes. And then finally, I want to close with some open questions. Right? So what should we think about now? I think there's really still a lot to think about. Most broadly, right, this is not really like a super limited, concrete, open question, right? But just generally, what are the foundations of game theory for AI systems, advanced AI systems, right? I hope I've convinced you that maybe in some ways it looks different than it would look for human beings or even corporations and so on. More specifically, there are these questions related to program equilibrium, which I hope many of you will go to Casper's practical tomorrow. And there are lots of variants there, right? Like what if you know, and also this last issue of playing with your twin, right? Maybe you don't actually, right? This idea that I can just read the other player's code maybe isn't always realistic, right? Like if I, let's say self-driving cars, if you give me the source code of a self-driving car, I probably can't really figure out a whole lot about it. I can maybe simulate it. In other cases, maybe I don't even have access. Maybe in some cases, I just get the parameter values of some huge model. What am I going to do with that? So it seems that a lot of these techniques get a little bit more subtle. I think that notion of simulation is a good one in the sense that like probably at least you can do that. But there may be other questions as well. Like what if you know you were trained in similar ways or that you have some overlapping parts of your source code? What should you do in those kinds of cases? Should we always make everything visible? Like with the self-driving car, it doesn't really seem to make sense that in order to know what it's going to do, I'm going to like look at all of its source code. That seems silly. It seems like more I need to know something about it at a meta level. And how do we think about that? I also want to think about what design decisions, and in particular like the architecture of the agents, will improve cooperation. Right? Maybe there's this idea that transparency would help, right? Or allowing players to be simulated would help. But sometimes that's a little bit subtle as well. And then there are related questions about like in what environment should we be running these agents, right? Maybe you want to argue that, well, maybe they should run in a blockchain environment because there we can really commit them to certain kinds of actions, make them transparent. Maybe, right? But I think that's a good question to ask as well. How should we think about the environments within which we deploy agents? And then finally, there are lots of interesting questions about how this interacts with learning systems, right? Can agents learn to do something like in the program equilibrium setup? Could you somehow naturally converge to that kind of cooperation? And also, how do you deal with these kind of paradoxes of self-reference where I'm thinking about a copy of myself? I hope you can sort of easily imagine that that's going to lead to uncomputability issues. And that paper I mentioned briefly earlier in TARC this year is really, I think, a very nice one for having a framework for thinking about those kinds of questions. Okay, I think with that I'm out of time. So thank you very much. And we'll take any questions.
All right, thanks, Vince. We've got a bunch of questions in the Slido. If you do have any more questions or you want to vote on the questions that are already there, please do. So the one at the top of the list at the moment is, it says, seems like large language models or any capable model are trained against large amounts of human data and pick up human biases. Should this inform the game theory we care about?
Good question. And should it affect what we train them on as well, right? I think, of course, large language models for now, as far as I'm aware, aren't truly agentic and are just kind of mimicking what we're doing. And to the extent that we defect on each other, maybe they're going to defect as well just because they're trying to predict what we would do. So that's one issue, right? So that's somewhat different from an agent that's really seeking to do specific things. But yeah, so I think this somewhat gets at this last question here, that we really want to think about the environments in which these agents are learned, are trained, and what they pick up from that. What kind of interactions do they have? And would that naturally steer them to be cooperative or not, right? I think large language models today aren't truly agentic, that they're trying to pursue something in the real world. And this talk, of course, has been more about systems that would do something like that. But maybe the distinction, won't be that great forever, right? And maybe at some point they will be trained in a somewhat more agentic way. And I think it's very important to think about how to do that. right? What is kind of the training data on which you do that? What are the environments within which to train them? How does that all interact with each other? Also, what do they learn about human beings in terms of how it's going to interact with us? Yeah, lots of more questions than answers, but I think that's a good one.
Nice. The next question I'm going to skip to is actually kind of quite closely related to the thing you just mentioned, which is can the kind of open source cooperation you showed be used to solve cooperation problems in the real world? Has it been applied in any real world scenarios so far that you know of? I also have something to add to this answer, depending on what you. I might have something to add to this answer, depending on how you answer it, because there's a.
So I think that's, this is mostly still theoretical work, but I do think it's important to think about these kind of learning setups, right? That in many contexts we wouldn't just expect everything to be so coordinated that everybody deploys the exact same program, and because of that everything is very stable. I would worry about, in one context, one program emerging and a different one emerging, and somehow these things clashing with each other. So do you need some kind of joint training or interactive training? What kinds of training will get you to something close to this kind of program equilibrium solution in a good way? I think there are still lots of open questions there, but we do have one paper that's, I think, under submission right now called Similarity-Based Cooperation. If you search for that, you will find it. That's trying to get at some of these issues and starting to make some headway.
Cool, nice. And the thing I was going to add is that recently some people who have been working in the kind of space of kind of crypto economics and things like this, where there are basic ways where kind of certain kind of amounts of kind of value can be kind of extracted by people kind of sniping each other and kind of basically locking each other into these competitive dynamics. Some of these can be avoided with kind of interesting cryptographic commitment devices, which actually rely on some of the protocols and things that Vince was kind of describing in his talk. And I think Casper might touch on that in the practical at some point. We ran a workshop with some folks working on that side of things earlier this year in conjunction with AMAS. So yeah, that's one kind of interesting space where that might suddenly start to take off quite soon. But yeah, that's just something I wanted to mention. So kind of big, I guess broad question is currently the one listed at the top at the moment, which is, what is the theory of impact of this research? How do you expect it to eventually make a difference in the real world? Which again, I think takes back to some of the other
Yeah, good. So we hope that this leads to better outcome, right? And I think I hinted a little bit at that early on, that we're worried about these fairly game theoretic tragedies somehow emerging and suddenly taking off into a direction that is really horrible and that nobody really understood, right? Like if we go back to the Amazon sellers, now there maybe the issue was that the algorithms were not intelligent enough to some extent, but I think it's a good illustration of, it's probably something that neither of the programmers ever expected to happen, right? You only kind of realize after the fact that, oh yeah, like after the fact this makes a lot of sense, but probably the moment you deployed it, you'd never even thought of such a thing, right? And I think that's the kind of thing we want to get on people's minds, to think about these issues of interaction, especially as it comes to AI systems pursuing goals. Many people in the world aren't that familiar with tragedies of the commons type of scenarios, and so that's, I think, a good one to have in mind and to also be providing solutions for. That said, I think we do want to be careful, right? Like Lewis and I and others have had many discussions about, well, how do you make sure that cooperation sounds good, but you also want to maybe avoid two agents colluding against a third, right? Especially if it's maybe two AI agents colluding against humanity, like that would not be good. And so I think that there is a lot of value for now still in just getting less confused and trying to figure out which of these aspects we really want and which ones we don't, and also how do we make differential progress towards the aspects that we like in cooperation, right? As opposed to maybe the sort of bad collusive outcomes as well. So I think for now, I hope I gave a little bit of intuition about our theory of change, but I also think it's important to get less confused, and as we do, maybe we actually update our theory of change a little bit as well.
Okay, cool. So final question I'll ask, currently at the top of the stack. How worried are you about incentivizing models to simulate humans well? Are you worried about this accelerating deceptive capabilities?
Good. I do worry about that for various reasons. You can actually if you want to follow me on social media, then like a somewhat unrelated thread, yeah, you can check what I'm thinking there. Most of this, now maybe in some sense, this would actually go in the opposite direction, right? If we make it really easy for AI agents to inspect each other, that will maybe prevent them from having the incentives to learn how to model agents that are not transparent to them, right? I hope that made some sense, right? Like that's, because in these kind of contexts, in principle, it can be very easy to simulate another agent, right? If an AI agent, if you have access to their code or even just a compiled version, it's straightforward to simulate them in a way that presumably it's not straightforward to simulate a human being, right? I don't know, if we all get electrodes implanted into our brains, maybe it changes. But for now, I think that's a different type of simulation, right? That's the kind of simulation that we as human beings do all the time. I had the slide with the brain. But of course, to some extent, we do run kinds of simulation of each other, and sometimes it works, right? Like sometimes my sister looks at my face, she's a psychologist, and like surprisingly rapidly, she knows what I'm thinking that I actually didn't want her to know. And so to some extent, we have this capability, but I would say it's a different kind of simulation from the ones that we're thinking about here, where an agent is completely transparent. So it's not clear to me that making them transparent in that way would somehow contribute to them becoming better at reading human beings as well. If anything, maybe it actually goes the other way, that it reduces the incentive to learn such things.
Okay, cool. Those are all the kind of questions we have time for. So one more round of applause for Vince, please. Thanks.